So here's some examples. And these are all Calculus 1 type examples. That's where I'm going to start, just to remind you of the kind of things we can have for one variable. So the function x cubed minus x kind of looks like this. And this is a polynomial. And polynomials are continuous everywhere. Okay, so hopefully you remember that from like Calculus 1. Anytime you're looking at a polynomial, you can expect that there won't be any discontinuities anywhere in the function. And if there's no discontinuities, then anytime you're asked about a limit, you can just plug in the value, right? And so if I were to ask you about, like, for example, the limit as x approaches 1 of x cubed minus x, you just plug in 1 cubed minus 1, and then you find the limit 0, right? So super easy for continuous functions. For this function, the next one that says g of x, this is x divided by absolute value of x. And so whenever x is positive, good morning. Whenever x is a positive value, then this is just going to be the same number in the numerator and denominator. So whenever x is positive, this is going to be constant at positive 1. Whenever x is negative, you'll have a negative number divided by the same value but opposite sign positive number. So it would be constant at negative 1. Whenever x is equal to 0, this is not defined because you can't divide by 0. Be 0 over 0. Right. So it'd be something like this. This is what I normally call a jump type discontinuity. And so if I happen to ask you about the limit as x approaches 0 of this function, x over absolute value x, then I would say that this limit does not exist. And you could just write the initials D and E for does not exist. I know what you mean. Okay. For this next function, the 1 over x, we're all very familiar with what this looks like, but I'll draw it. 1 over x has this kind of shape to it. That's not the perfect drawing, but it's the idea. So as x is getting closer and closer to 0 and x is positive, this is going to be a very, very large positive number approaching infinity as you get closer to 0. And then if x is a negative number and x is getting closer to 0, then this becomes a very, very large negative number approaching infinity as x approaches 0 from the left side. And so if I were to ask you about this limit as x approaches 0 of 1 over x, again, I would say that this does not exist because the right side limit is going to plus infinity, the left side limit is going to negative infinity, and this is what I call a pole. The next example has another kind of pole. But in my next example, I have 1 over x squared. And so since x is squared, this always has to be positive. So we'll still have this kind of vertical asymptote or pole happening. But in this case, I think it would be valid to say that the limit as x approaches 0 of 1 over x squared could be plus infinity. Right? you're not approaching any given number, but at least the right side limit and the left side limit are approaching the same kind of infinity. They're both going to plus infinity. Okay, so this example where I have sine of x over x, this function kind of looks like this around origin. And actually, if you just plugged in x equals 0, and we set x equal to 0, this would be sine of 0 over 0, which would be 0 over 0. So the function is not defined at x equals 0. But if you take the limit as x approaches 0 of sine of x over x, one thing you can think about is L'Hopital's rule. So L'Hopital's rule says that since this is an indeterminate form, 0 divided by 0, you could take the derivative of the numerator and the derivative of the denominator separately and take the same limit. So the derivative of the numerator would be cosine of x. The derivative of the denominator would be 1. And so the limit as x approaches 0 is now 1. And so while this function is not defined here at the point x equals 0, the limit is well defined. So in this case, I call it a removable discontinuity. And specifically, I like the word removable because this discontinuity could be removed. What if I defined another function, g of x, and g of x is going to be a piecewise function, and for the first piece of the function I say, well, if x is not equal to 0, then sine of x over x. And if x equals 0, then 1. So this function f of x is like not continuous. It's not continuous because I have that removable discontinuity at x equals 0. But this function, g of x, is continuous. Because all I've done with my piecewise function g of x is I just removed the discontinuity. I just said, okay, well fine then, g of 0 is 1. And then you're good to go. Okay, so that was just a quick review of Calculus 1 limits. Everyone feel good about those types of discontinuities that you could come up with for one variable? Because it gets a little bit weirder when we have multiple variables. We have these multivariable functions. So here we go. I've got g of x and y. So this is a multivariable function with 2 input variables. But this function is just a polynomial of 2 variables, right? I just have natural number powers of my independent variables. And so this is going to be continuous everywhere. Since this is a polynomial, of 2 variables, it's also going to be continuous for the same reason that in Calculus 1, if you had a polynomial, you knew that that polynomial was continuous everywhere. So any limit I take here, if I take the limit as x, y approaches, 1, 1, all I have to do is just plug in x equals 1, y equals 1, and then that's how you just calculate your limit. So super easy, no question there, right? And if I were to plot this, I'm going to go ahead and plot everything we do today on GeoGebra. I can say z is equal to x squared minus y squared. And so I get a surface And the surface doesn't have any weird discontinuities. It doesn't have any poles, it doesn't have any removable discontinuities, it doesn't have any jump discontinuities, it doesn't have anything strange going on. Cool. All right. New example. Whenever I look at this, I've got stuff going on in my denominator, and I know I can't divide by 0, right? So if I ask you, a question that looks like, what's the limit as xy approaches 0, 0? I can't just plug in zeros. That doesn't help me. What you might do, and this is just an idea, is you might try to take limits going at different directions at the problem. So what I mean by this is like, what if I said, let's try the direction or the path where I have x is equal to 0, then I would have 1 over 0 times y, and then I could think about the limit just as y approaches 0. Of course, that does not exist, because I can't divide by 0. I also might try a different direction. I might try to say, well, what about the direction when y is equal to 0? So I'm trying to go along the direction of just the x-axis and see what happens with my function. Same deal. Then I would end up with a simplified limit where I'm just only thinking about x equals 0, but it would be x times 0, so that does not exist. And just pretty good evidence here that this limit doesn't exist. In fact, if you just find one of these where the limit doesn't exist, you can call it good for a multivariable function. We're going to try some other directions and some other examples, but for this example, like I said, as long as you find just one direction where the limit doesn't exist, then you know the limit doesn't exist. And so this is a pretty chaotic example if I show you the graph of it. This is the surface z equals 1 over x times y. And as you're approaching the origin from any direction, the limit doesn't exist. If I tried, let's try one more. Like, what if I try the direction x equals y? And maybe I should be more specific about what we're doing whenever I try a direction. So like, here's my my space, my xyz space. Whenever I tell you we're going to try the direction x equals y, what I'm saying is just in the xy plane, there's a line that represents x equals y. This is the x equals y line. And so I'm saying, let me take a trace of my surface along the plane defined by x equals y, and then I'll take a look at what the limit is on that trace. And here, what we're doing is, whenever I say if I try the direction x equals 0, the same idea. So I could just say the y-axis, that's the line where x is equal to 0. Crap. The y-axis, this is my line where x is equal to 0. And so if I take the trace of my surface in the yz plane, where x is equal to 0, and then I can think about the limit just in terms of y, it makes my problem just a little bit simplified. So let's take the trace of this surface, and I'm still talking about the surface 1 over xy. If I take the trace of that surface in the plane where x is equal to y, then now I could rewrite this as 1 over x squared, right? Because I just said x is equal to y. Let me just replace the y with an x, and then I get 1 over x squared. And now I can think about the limit as x approaches 0. But this is, I mean, it's still not a well-defined number you're approaching, but at least you're approaching the same infinity, right? Okay, so that's not too bad. And then one more. What if we try the direction x equals negative y? So if I start with my surface and then I replace x with a negative y, I would get 1 over negative y squared. And if I take the limit as y approaches 0, this would be approaching negative infinity. So in my xy plane, the line x equals negative y would be like this direction. And so again, I knew my limit didn't exist because I tried just, the trace in the xz plane and it didn't exist, and I tried the trace in the yz plane and it didn't exist. But this is also further evidence that it doesn't exist, because these two limits, when I took the limit on a different trace of my surface, I got limits that were different. And so since I'm getting different limits, then you still say that the limit doesn't exist. We only say that for a multivariable function, we only say that the limit exists if the limit is the same on every single trace of the surface. And so clearly that's not what we're getting. We're getting a lot of problems here. Let me show you what the plane x equals y looks like on GeoGebra. So that's my plane x equals y. And if you just think about the trace, so the intersection between my red surface and my blue plane here, if you just think about the trace, then as x is approaching 0 here on the intersection, it's going up to plus infinity and going up to plus infinity, right? That's why I said the limit there was plus infinity on that particular trace. But if I set the plane x equals negative y, then I get this plane, and the intersection of the red surface with this blue plane as x approaches 0, or as y approaches 0, same thing, it goes down towards negative infinity as you approach that origin. So that's why I had that limit of negative infinity. In any case, that was a pretty chaotic example. Let's do another one. I've got lots more examples today. That's a little bit small, so I'll rewrite it. This says that I have the function g of x, and it should be g of x and y. Two-variable function is 1 minus cosine of x squared plus y squared divided by x squared plus y squared. So again, this is a function of two variables, so I can think of it as a surface in 3D space. And if I wanted to consider the limit as x and y approach the origin, the limit as I get closer and closer to the origin in my xy plane, if I want to know what the limit of this surface is, it's going to help if I think about it along a few traces first. So the first thing I might do is try the trace on the plane where x is equal to 0. Remember, x equals 0, that's also called the yz plane. And then I might try the trace on the plane y equals 0. That would be the xz plane. And then I might try the trace on the plane where x equals y, and then try the trace on the plane where x equals negative y. By the way, there's a lot of other traces you could try. You could try x equals 2y, or x equals negative 2y, or x equals 1/2 y, or x equals negative half y. There's actually infinitely many vertical planes you could try. And I'm going to revisit that and talk to you about that more later. But I just like trying these 4 traces and seeing what happens with the limit, because it helps me get a better grasp of what I'm looking at. And a lot of times you can get a lot of insight about a surface from looking at those 4 traces. And in this case, let me try setting x is equal to 0 first. And if x is already equal to 0, then I'm going to be thinking about the limit as y approaches 0. And this is going to be the function 1 minus cosine of y squared over y squared. Again, because right now I'm trying the trace in x equals 0. So as y approaches 0, I can't really tell what's going on yet, but remember the limit of a constant is just that constant, and if I'm taking the limit of 2 things that I'm adding or subtracting, the limit of 2 terms, limit rules allow me to separate that. And so I can just easily make this the limit of 1, which is 1, minus the limit as y approaches 0 of cosine y squared divided by y squared. And as y is approaching 0, what is cosine of 0? 1. And then that would be 1 over 0, which doesn't exist, and it's not an indeterminate form, so I can't use L'Hopital's rule or anything like that. This is going to be a case where cosine, as y is approaching 0, the cosine function of that is going to be approaching positive 1 on both sides. It'll be positive. And then in the denominator, y squared is always going to be positive, but approaching 0. So this is going to blow up towards positive infinity. And so since I have 1 minus something that's blowing up towards positive infinity, this is going to be a limit of negative infinity. Okay. But that was only in the trace of the plane x equals 0. And so that only gives me a piece of the picture, right? It might be different if we try y equals 0. Maybe it'll be the same. Maybe it'll be different. We don't know. And I can actually tell you ahead of time that this is going to end up the same, because this is symmetric with respect to x and y, right? You can change x and y and it doesn't change what this is, right? I could say y squared plus x squared, it doesn't matter what the order is. Addition is commutative. And so since this is symmetric with respect to x and y, if I took the limit as x approaches 0 of 1 minus cosine x squared over x squared, then this limit is also going to be negative infinity. Okay? Let's try x equals y. And if I take the trace in the plane x equals y, then I'm going to be taking the limit. Let's say I replace all my y's with x's, and so I take the limit as x is approaching 0 of 1 minus cosine of x squared plus x squared. Yeah, I'm replacing y with x. So I say x squared plus x squared, that's 2x squared over x squared plus x squared, that's 2x squared. But even with that, even with that 2 present, as x is approaching 0, I still have a situation where I'm approaching positive 1 on the left and the right, and I'm approaching 0 from a positive direction on the left and the right in the denominator, so 1 over 0. It's still blowing up to infinity, so 1 minus something blowing up to positive infinity is going to be negative infinity. And then likewise, if we do the trace, where I say x equals negative y, I still have the same situation where, let me replace every x with a negative y, and then I'll have cosine of, well, since I'm squaring it, it doesn't really matter. It would still be negative y squared plus y squared over negative y squared plus y squared. So whenever I take the negative y and then square it, it's the same as positive y squared. And so this is just, again, the limit as y approaches 0 of 1 minus cosine of 2y squared over 2y squared, and we already know what that is. It's negative infinity. And so here, I took the limit as x and y approach 0 along 4 different directions, 4 different traces in different planes. And so this gives me a pretty good clue, like a pretty good idea that the limit of this is probably going to negative infinity from every direction. But, and this is really important, it is not proof, right? In fact, no matter how many traces you take, whether you take 100 traces or 1,000,000 traces, it's never proof that the limit exists. There's a way to do a proof. It's called epsilon delta. I'm not going to bother with that because this is not an analysis class, and so I don't want to teach you, I don't want to go through that effort myself. If you're going to study math, you'll take an analysis class. If you're not going to study math, then you never have to know about epsilons and deltas, and so we're just going to leave that. But taking these 4 traces from these 4 different directions is going to give me a pretty solid idea that, yeah, the limit is probably negative infinity. Even though it's not solid proof, it's still a pretty good clue. So let's plot this surface in GeoGebra and see what it looks like. So here is...
So how many different directions are sufficient for...
There's not a number.
For the purpose of this in a test.
I'm not going to ask you to... One question I might ask on a test is, by taking the trace x equals 0 and y equals 0, can you prove that the limit does not exist? Because if you take a trace, if you take one trace and the limit doesn't exist, then the limit doesn't exist. Okay? If you take 2 traces and you get that the limit exists, but you get different limits, like the first trace and the second trace you take arrive at different limits, then the limit doesn't exist. And that's solid proof that the limit doesn't exist if you have that situation. The only thing is, if you take 4 or 6 or 10 traces and the limit is always the same, that's still not solid proof that the limit exists. I'll write this later. I want to work a few more examples, and then I'll go I'll try to be more clear about what I mean. But
I see an example where you take a lot of limits and you find the same, and then there's one that doesn't work.
okay, cool. So this is what that surface looks like, the function we were just messing around with. And it's, radially symmetric about the origin. And so you can kind of tell now by looking at it that surely no matter what direction you came from, the limit is the same. It just falls into that sinkhole and goes to negative infinity. So what we were doing whenever we were just messing with those limits from each of the traces, as I was saying, what about the plane where x equals 0? You know, if I just looked at that intersection, it becomes a single variable function, and then I found that the limit was negative infinity. And what if I change the direction and I say, instead of x equals 0, what about the plane y equals 0? And again, we found that the limit in that intersection was negative infinity. And changing directions again, what if I say I want the plane x equals y? That trace was also negative infinity. And changing directions again, if I say x equals negative y, that's a different plane, and I also said the limit was negative infinity. So this is not solid proof, but what we did in total was like this. We looked at all 4 of those planes, and in those planes, the traces all had the same limit, negative infinity. So it's a lot of evidence, but it's just not proof. Okay. So here we go. New function, xy over x squared plus y squared. Let's try to take this limit as any point approaches the origin of that. And so we're going to try out my favorite traces. We're going to try the plane where x equals 0 and then y equals 0, x equals y, and then x equals negative y, and we're going to see what we get each time. So for x equals 0, this trace is going to give me the limit as y approaches 0 of 0 times y divided by 0 squared plus y squared. So this is the limit as y approaches 0 of 0 divided by y squared. Which is actually an indeterminate form, right? So 0 over 0 gives me an indeterminate form. So that means I can use L'Hopital's rule. And L'Hopital's rule says take the same limit, but derivative of numerator, derivative of denominator. So the derivative of 0 is 0. The derivative of y squared is 2y. Okay. It's still an indeterminate form, so I can apply L'Hopital's rule a second time. And applying L'Hopital's rule a second time gives me 0 over 2. So this limit is 0. Okay. Very good. Let's take the trace y equals 0. And you can probably already tell what's going to happen here because x and y are symmetric. Multiplication's commutative, addition's commutative. It doesn't matter what the order is. If I set y equals 0 and do this trace, it's going to end up the same way. It's going to end up being the limit as x approaches 0 of x times 0 divided by x squared plus 0 squared. And eventually, after you apply L'Hopital's rule twice, you'll get the limit is 0. So we're starting to think, yeah, we've got a little bit of evidence that the limit as we approach the origin of the surface is 0, right? That's 2 traces now where the limit was 0. That's some evidence that we're collecting. Now, let's try another trace. We're going to try the trace where x is equal to y. That limit was 0. That limit was 0. What about x is equal to y? That's just another plane that we can take the trace in. And if I set x equal to y, then this limit is going to be like x approaches 0, and we'll just replace all of the y's with x's now. So this would be x times x over x squared plus x squared. And so that's the limit as x approaches 0 of x squared divided by 2x squared. So that is the limit as x approaches 0 of 1/2, which is 1/2. So that is not the same limit when I took a new trace. And so immediately, whenever you get something that disagrees, you take a trace and you get something that disagrees with the other traces, that immediately tells you the limit does not exist for this function, okay? Just for the sake of instruction, we're going to do the last trace that I like to do, which is...
It was the 1 on the top.
Huh?
From where did you get the 1?
X squared over 2x squared?
Oh, okay.
If I just divide the top and the bottom by x squared, then x squared over x squared is 1, 2x squared over x squared is 2. Yeah. Okay. So the last trace of my favorite traces says I'm going to replace all of my x's with negative y's. And so this would give me negative y times y over negative y squared plus y squared. So this is the limit as y approaches 0 of negative y squared over 2y squared, which is the limit as y approaches 0 of negative 1/2, which is negative 1/2. Okay, so just to recap, the 4 traces that I like to do gave me 0, 0, 1/2, negative 1/2. And since I'm not getting all of the same limits, then this limit does not exist, okay? The answer to this problem would be D and E. Again, I want to show you, and I think it's really good, as you're doing your homework problems, go back to GeoGebra when you're done and just see what it looks like. So let me plot this function that we've been dealing with here. So the numerator should just be x times y. Hate GeoGebra. I mean, it's useful, but like Desmos is so much easier to use. Ugh. Okay, so I'm just going to delete this and start over. Z equals xy divided by x squared plus y squared. Okay. Oof, they give me a weird color. So I really want to change that color. That's better. Kind of. So here's what it looks like. It kind of gets pinched around the origin a little bit. Like it's kind of flat as you go far away from the origin. But let's talk about the first trace that we took. We took x equals 0 first. And whenever x was equal to 0, the limit was 0. So it's like if we were traveling along this black line that I added. Do you see how the black line actually coincides with the green curve, or the green surface everywhere? And the value of z here is 0. And so as you're approaching from the origin, from the left side or from the right side, all of the values are 0. And so if your sequence is 0, 0, 0, 0, 0, then the limit's 0. And that's what we found with our algebra skills. Okay? Then the next trace we took was setting y equal to 0. And so that would look like this. Again, same thing. All of the values are 0 if you take the trace where y is equal to 0. So of course the limit is 0, and that's what we found. If you take the trace where x is equal to y, we found that the limit was 1/2. And that would be like traveling along this little black line here. So if no matter whether you come from the left side or the right side, all of the values here have z value 1/2. And so as you're approaching the origin, it's just 1/2 all the way. So of course the limit's 1/2, and that's what we found. Lastly, if we were taking the last trace where I set x equal to -y, we got the limit -1/2, and that's like if you traveled along this line. No matter if you're coming from the left or the right, all of the values were -1/2 all the way, so of course the limit at the origin was -1/2. So this is something that can happen with multivariable functions, where you can take a bunch of different traces and get sometimes the same result, sometimes different results. And so it's not enough just because you've taken the limit in 2 different traces or 3 different traces or 4 different traces. Even if you get the same limit, that's still not enough to prove that that limit exists. It's just kind of like collecting evidence, you know, but never quite enough to prove it.
How to algebraically define symmetry in 3D?
Symmetry?
Yeah, like the symmetry of a graph.
Like, are you saying like, why did I say this was symmetric between x and y?
Like in general, I'm going in general right now. Like, for example, in 2D, you say if the function satisfies f of x is equal to f of -x is even and all that, and so it's symmetric about the y-axis. Can we say the same thing?
Yes.
Really?
Mm-hmm. Yeah, you can. All those rules still apply. So I've got 7 minutes left. The last thing that I really want to show you is this. Let me revisit this one. Just gotta erase what I did earlier. One really, really powerful tool that we have when it comes to taking limits, especially, well, really, only whenever the limit is approaching the origin. That's a lot of times what we're concerned with. If your limit is approaching the origin, it can be really, really good to switch to cylindrical coordinates. It can be really good to switch to cylindrical coordinates. So, like this function is g of x equals 1 minus cosine of x squared plus y squared over x squared plus y squared. And the conversion from rectangular coordinates, x, y, and z, to cylindrical coordinates, which is r theta z, that conversion goes like this. You say r is equal to square root of x squared plus y squared, theta, tangent theta is y over x, and then z is z. Okay, so in this function, the function value you can think of as z if you're thinking of it like a surface in 3D space. But what I'm really concerned with is just replacing this x squared plus y squared with what? R squared, yeah. And then the denominator would be r squared. And so now, if I wanted to take the limit as x and y approach the origin, I could take the limit as r approaches 0. R is the distance from the origin. And as long as I don't specify what theta is, then this is a good generalized limit saying we're approaching the origin from, hey, any direction. Theta can be whatever the hell you want. So like it doesn't matter, right? And that's really, really cool because this at the same time is taking the limit from like every direction. This is actually a way that with some multivariable functions you can prove that this limit does exist. So we're taking the limit as r approaches 0 of 1 minus cosine r squared over r squared. Limit rules tell me I can take the 1 minus out, and then as I take the limit as r approaches 0, this is cosine of r squared over r squared. And I've kind of repeated myself a whole lot today, but remember that this r squared is always positive, so we're talking about the cosine function approaching an argument of 0, but it's always positive, so we're approaching positive 1 in the numerator. And in the denominator, r is approaching 0, so r squared is approaching 0. Since it's squared, it's always going to be positive. So we're talking about positive numerator, positive denominator. Numerator is approaching 1, denominator is approaching 0. So the ratio there is approaching positive infinity. If I have 1 minus positive infinity, then this limit is negative infinity. And since we're using this kind of line of reasoning where I switch to cylindrical coordinates, and I didn't specify a theta, I didn't specify what direction we're taking this limit in, this is actually proof that this limit is negative infinity. We're not just taking a few directions, we're not just taking this trace and this trace and this trace, but by switching to cylindrical coordinates, we're taking, all infinity traces at the same time. We're approaching this limit in every direction. And that's pretty cool. So, limitations of the cylindrical coordinates thing, though, is that it only allows you to take the limit as you're approaching the origin. You can't switch to cylindrical coordinates and take the limit as you approach like 1, 2, because you can't just say r is approaching 0. So that sucks. And again, you won't be able to use this with every function. We were only able to use it with this function because we had x squared plus y squared everywhere, and that's really easy to just replace with an r. But if this function were instead cosine of x plus y, now you can't really switch to cylindrical coordinates because you don't get really nice clean functions of just r. The deal here is you have to be able to make the substitution and have a function of just r, and then take the limit as r approaches 0. So only a few cases where that's useful, but where it is useful, it's really, really powerful.